Good afternoon to all the participants. My name is Dr. Malik. A very warm welcome to all of you in this webinar. Although it has started to get little chilly in North India, but still from our side, from the organizers, Bulk Solids Innovation India and Thapar Institute, a very warm welcome to all of you for being here this afternoon. Today our topic is, does poor ash discharge or poor ash flow from the ESP hopper make you suffer? We often talk about poor ash handling systems working in the power station, and we frequently say that it is the compressor or vacuum pump or maybe the small pipe which is a problem. But we only can question the capacity of compressors or vacuum pump if the ash falls in the line first. That means the ash first has to fall from the ESP hopper to the pipeline. If the ash doesn't fall in the first place to the ESP hopper, we are in problem. So today we thought that this is a topic which people normally do not pay attention to. We often assume that everything is fine at the ESP hopper and ash would fall irrespective of its properties, but it may not be the case. So today we are going to talk about this problem and see some of the solutions. We will also try to understand the mechanisms of ash discharge. In fact, how the powder flow happens through hoppers. To start with, I will give a little introduction about our laboratory. This type of introduction I have already given in the past, so I will try to be as brief as I can. We are associated with Thapar Institute of Engineering and Technology. We work in the powder flow laboratory. In our laboratory, we have very sophisticated powder characterization tools, some of which I will share with you later in this presentation. Also, we have one of the largest pneumatic conveying test setup around, at least at the institute level. In our lab, we could convey ash at a very high rate. For example, fast field ash we can convey at 50 to 60 tons per hour, which is quite high for any laboratory setup. We work in the area of fine powder flow, pneumatic conveying, flow through the hoppers, and our specialization always has been fly ash. This is a material on which we have conducted research over the years. There are several industrial partners who have worked with us in the past from Thapar Institute, and I take this opportunity to thank all of them. Department of Science and Technology, Government of India, CSIR, NTPC, one of our biggest sponsors for research. Very big thanks to them. Also GRANU Belgium. We are doing some projects with Tata Power. Right now also Odisha Power Generation Corporation, Aditya Birla Reliance Group, and Haryana Power Generation. These are some of our industry sponsors. We have been working in the research of powder and bulk solids for quite some time, but then we also thought, how can we take our technology out to the industry for the benefit of industry? How can we provide innovative solutions to industry? And quite coincidentally, last year when we were thinking about this, how to do that, the MHRD and AICT, they came up with this policy for National Innovation and Startup Policy for faculty and students. And under that policy, or following that policy, we came up with our startup, which is Bulk Solids Innovation India Private Limited, which is a technology-based startup. And right now we are focusing on providing solutions to the power stations in terms of designing and mainly troubleshooting ash handling systems. So in our company, I'm one of the co-founders along with Dr. Kundan and Dr. Atul Sharma. We also have Dr. D.S. Malik, who has recently joined as a director. He has large experience in DCPL and DCIPS. We also have senior advisor, Professor Peter Whippich from the University of Wollongong, Australia. BSII, Bulk Solids Innovation India Private Limited, is a university-based startup located at Thapar Institute of Engineering and Technology, Patiala. We are providing design, as I said, troubleshooting, that's on top of our agenda, as well as EPCM solution. So we can find the root cause of your problem, or we can do the troubleshooting. We can recommend the solution options, of course optimized, and then we can do the entire EPCM part, and we hand over you the improved plant. So that's our agenda. We have also received grant in aid. I mean, BSII has received grant in aid from the government of India to develop, to further develop the ash handling and ash utilization technologies, so that our power stations can get some relief from this highly contemporary area, which is a problematic area. Now, being at Thapar Institute helps us in many ways. An institute atmosphere nurtures creativity and innovation ecosystem, and so you can be assured of that our solutions would be reliable, credible, and there is always integrity in our solutions being associated at the university. So we are once again at the Science and Technology Entrepreneurs Park in Thapar Institute of Engineering and Technology campus. Very recently, we have also got a prestigious recognition from the Government of India, from the Ministry of Commerce and Industry Department of Promotion. We have been recognized as a startup by the Government of India. So I'm just sharing with you the certificate. You can see right here on the screen. Today we are going to be three persons sharing our experience and knowledge with you. Myself, Dr. S.S. Malik, and I'm the founder and director of Bulk Solids Innovation India. I am associate professor at Thapar Institute in the Department of Mechanical Engineering. We also have Professor Peter Whippet from the University of Wollongong. So he's a senior advisor to BSII, our company. And we also have another director, Mr. D.S. Mullik. He has 45+ years of experience in DCPL and DCIPS. In many ash handling projects he has worked on for NTPC state and private agencies. Now we start with a very basic question. Today the topic, let me once again remind, this is all about ash flow through the ESP hoppers. The first question we have to ask ourselves is, why would ash not fall in the first place? I mean, won't it fall by gravity? So you have ESP hopper, which is full of ash. So the ash should fall by gravity, and then it should enter into the vacuum conveying line when the material discharge valve is open. Now it should happen automatically, isn't it? That's what we think. However, it doesn't always go that way. So ash does not always spontaneously come out by gravity. There are reasons for that, and we are going to see those reasons. But at least you know that it's not automatic, it's not spontaneous. Hopper flow, whether it is fine powder, whether it is coarse products, whether it is fly ash or some other powders, is not something which is a very easy thing to design. Not everything that goes in comes out, and that's been the problem. And people do all sort of things. They hammer it, they put air cannon, they put fluidizing pad, they do this and that. But then if the things are not correctly designed at the first place, then the level of problem may be beyond in any sort of rectification at later stage, and the problems can become quite chronic in nature. Now, before I go further, I would just like to go through some basics. We categorize hoppers in two ways. One is the mass flow type hopper and funnel flow type hopper. Now, mass flow type hopper means where the entire mass of the hopper comes out in first in, first out basis. That means the material which has gone in first, it will come out first. These hoppers typically have steep angles. They are more taller, and the wall friction is typically less, so that would promote the flow. And as an advantage, you get uniform discharge property, and the retention time is also low. Whereas the funnel flow hopper, on the other sides, the angle is shallow. As a result, the material on the sides, they are supported by the hopper wall, and therefore you tend to have some dead zone building up, and only the core material, the material at the core, that's going to fall. So this is the core material which is going to fall, and you have material building up on the sides. And if it retains there for quite a long time, it can lose all its fluidity, and it may not even come out. So you may not be even using the full capacity of the hopper. Let's look into some of the problems. Number one problem is arcing, flow problem, arcing. So arcing is where at the outlet of the, just let me go back to this again. Yeah, arcing is where the material doesn't fall. So at the outlet of the hopper, which is at the bottom, you have a solid bridge formation, and that's because of the cohesive nature of ash. The ash has become too strong, or any powder is not able to come out. I'll show some pictures with you. The other one is funnel flow. Now, if the funnel flow becomes too extreme, then you can have dead zones building up on the sides of the hopper. Then you have rat hole. Now that's another extreme end of the funnel flow problem. You might have something like a long tunnel through the hopper, and you have absolute stagnant zones towards on both the sides, and it's only the core of the hopper which is working. So you can see that how much area of the hopper you are not using. You can also have segregation, typically can happen more in a funnel flow hopper. So the core part would be fine powders, whereas on the sides you would have coarser powders or coarser ash. So when the ash comes out, the properties are non-uniform. Sometimes you have too large ash, which is difficult to flow pneumatically. Sometimes you may have too fine ash, which is easier to flow. And your line can choke when you have all the coarse particles come out. So segregation is also another issue. All right, some example. Now this is what you see is actually arcing. So this is the outlet of an ESP hopper, and you can see the ash buildup and then cohesive nature of the ash. The material is just not able to come out. This is a picture, an example of rat hole, where you can see the light coming. That means you can see the outlet hole. So it's not arcing, it's rat hole where the opening is still there, but unfortunately ash has built up inside the ESP hopper. And the problem is when the ash builds up, the surface become distorted. So you can see the roughness of the surface. Now you're asking the ash to actually flow out against this high rough surface. So the friction is a lot more. So the ash will not easily come out and the problem will get bigger and bigger. Typically, the ash would start building up on the edges of the ESP hopper. So plain flow hoppers, otherwise all good. But the problem is you have sharp edges, and typically the ash would start to build on those edges. So these are some pictures taken from some ESP hoppers. They are real hoppers, and then these buildups become too much, and then eventually you have a blocked hopper outlet. So that's the extreme problem that you can have. Now let's look into the philosophy of hopper design. If you are a civil engineer or if you are doing civil engineering designs, your design is based on the hypothesis that the material must not fail, and your objective is that material must not fail. So if there is a beam or there's a column, it should not break. So in civil engineering, you design for not failure of the structure. Whereas if you are a powder technologist, just like me, and trying to design a hopper for industrial system, we design, or I design in such a way, my aim is that the powder must fail. So if the hopper is allowing powders to fall, if the ash is coming out of the ESP hopper, in this I would take the powder as a structure and I would make sure that the powder fails. So this is a design philosophical change compared to a civil engineer. My intention here that the powder must fail. Now let's look into some concepts. The first concept we are going to see today is wall friction. Now, in a very simplistic way, let's look into the forces which are acting in the hopper. Now you can see one is the weight of the powder. So the powder weight pushes the material downwards, right? So it is the weight of the powder or the gravity which will help you to help the powder to flow out. Now the walls will provide resistance, and the type of resistance we are talking about here is a shear resistance, and that would actually prevent the flow. When the powder is coming out of the hopper, it is sliding against the wall. So the wall is providing some resistance which is preventing the flow. So the weight of the powder is consolidating stress, is providing consolidation stress which is helping the flow. The wall friction is providing shear stress or shear resistance which is going against the flow. And there is always a battle between these two. One is trying to pull the powders down, one is trying to resist it. The second concept that we are going to talk about now is the concept of powder strength, and that's very important. This is where this is a little bit fundamental, but this is very interesting as well. So let's do an example. Let's go by 3 steps, and in 3 steps we are going to understand how the what we mean by powder strength. So you take some powder in a box, in a solid box, you fill up the solid box with some powder, and then you apply some stress on it. So what's going to happen? The powder is going to first get consolidated. So you apply certain stress, sigma. So sigma into the sigma 1. So that's a consolidation stress. So you push the powder down. On both sides you have the wall, so the powders can't escape. Step number 2. Then you remove the wall. Now what you are going to see, unless the powder is like sand, which is very free flowing, if you have fly ash or something which is fine, a little bit of cohesive, what you are going to see that even when you remove the wall, the material will hold its shape. Why? Because the powder has got some strength. I will come to that. How the powder gains strength, I will come to that later. But this is something physically we have seen. You all might have experienced this at some point. So you push the powder, you consolidate the powder, then you remove the sides, the powder has gained strength, so it will hold its structure. So even if the wall is not there, the structure is not going to get disintegrated because it has become strong. Now let's move to number 3 step. Number 3 step is where you apply some stress. So what you do is the powder was standing on its own because it got strength. Now what I am going to do, I am going to add a little bit of load on top of the powder. Maybe because of its strength, it will still stand strong. However, when I keep on adding the load more and more, there will be a point when the powder is going to fail. And that stress is known as the unconfined yield stress, or for the purpose of this webinar, we can call it in a very simple term, the strength of the powder. So to overcome the strength of the powder, I have to provide some load or some stress, and when that stress is more than the strength of the powder is going to fail. And when the powder fails, the powder starts to flow. And that's exactly what we want, that the powder should flow. So that's the flowing criteria of the powder. All right, so let's move on. All right. So something quite interesting and something probably we can intuitively think that when I increase my sigma 1, which is my consolidation strength or stress, that's the stress with which I have compacted the powder or pushed the powder down, that's sigma 1 in the x-axis. When I increase my sigma 1 or the consolidation stress, the strength which the powder has developed will also increase. So this is a strength versus stress diagram or consolidation diagram. So that means when you increase the consolidation, the strength of the powder will also increase. That's something we can think from our common sense. The more I push, the more solidified the powder will get. Now someone might think or might ask, why is it so? What's happening at the microparticle level? So let's just dedicate one slide for that. There are 3 forces which are working, mainly 3 forces. One is the van der Waals forces between the particles. One is the liquid bridges. Maybe there are certain moisture on the particle surface, and because of that there are some liquid bridges, and you also do have electrostatic charges on the particles. Now because of these, the particles, they stick together. They actually create all 3 forces. They create cohesion as well as adhesion on the wall. Generally, smaller the interparticle distance and smaller the size of the particles, the cohesion and adhesion forces would increase. All right. So when you are actually adding more stress on the powder by consolidating, what you are doing is you are pushing the powders down you are pushing one layer of powder, pushing it more closer to the next layer of powder just underneath, and that layer pushes it further down to the next layer and so on. So the interparticle distances are coming smaller and smaller and smaller. So your van der Waals forces would increase, your liquid bridges would increase, and which is caused by the moisture, as well as the electrostatic charges would increase. So because of this consolidation and the volume of the powder getting low, powders are coming close to each other. As a result, all these forces would increase, and because of that, the powders would become more cohesive, or in other words, they would gain more strength. Bulk density increases with consolidation. All right, so when you push the powders down, the same mass of the powder now has less volume to occupy, so obviously the bulk density is going to go up. Now, one very interesting point, the orange line, you can see the consolidation, which is because of the weight of the powder that actually is trying to make the powders flow out of the hopper. Now, more the consolidation, better for flow, because that is acting downwards. But more the consolidation, you also increase your sigma c, which is your strength. Now, for flow to happen, let me read it out. The flow to happen in very simple terms, the downward push or the consolidation stress must be higher than the lateral reaction, which is coming from the wall, and that's because of the powder getting strength and the wall friction. So the downward stress because of the consolidation must overcome these two stress components. One is the strength of the powder and the wall friction. Now you see, while more consolidation is better for the flow to happen because it's a more vertical stress, which is trying to push the powders out of the hopper outlet, more consolidation will also increase the strength of the powders. So you have a bit of a loopy effect. More consolidation, more strength, which is not good. More consolidation, more vertical push, which is good. So which one dominates over which one? That's where the powder technologies come into play. So we use, I'm not going to say much on this, it becomes a little bit mathematical, but we use a lot of strength of material formula. So we have our machine at the lab, which is powder flow tester, which works on the principle of Janicki shear tester. So we do deal with normal stresses. We apply normal stresses on the powders, then we apply shear stress, then we develop more circles, we deal with principal stresses, and from that we find out that what would be the hopper outlet opening, what would be the dimension of that opening, which is very critical, and what would be the slope of the hopper. Now these are the two things which are extremely important. Then we generate some diagram which is known as the flow function curve, where you have the stress and consolidation stress on the x-axis and the strength on the y-axis, and this whole diagram is divided into 4 parts. Not flowing, which is a very poor situation, very cohesive, easy flowing, and free flowing. In fact, 5 parts. So typically ash would be in the cohesive to easy flowing zone, and if it is cohesive, it becomes a problem. So this curve is typically known as the flow function curve. There are different 5 regimes based on the property of ash. Now one important point you have to remember, that when you load the powder for some time, the strength becomes more, and you can see the ash, the farm line is for instantaneous. Then the dash lines are when some time has passed, so you have loaded the powder, or in your term, I can say, in the power plant term, when the ESP hopper is full of ash for some time, there's a 2 hour, 4 hour, 6 hour, 8 hour, gradually the strength increases because of consolidation. So the tendency of ash coming out would also decrease because of the change in property of the ash, and that's known as time consolidation. We also sometimes see rat hole in the vacuum conveying system. So when you run the vacuum line in the power station, what happens is the central part, which is the fine ash from the core of the ESP hopper, comes out, and you do build up stagnant zones on the sides. So we have seen several cases like that in the ESP hoppers. So we have done some experiments at Thapar Institute where we provided fluidizing air on the side of the ESP hopper, and we actually broke those built-up layers, and we optimize the amount of air which is to be given. So you can calculate and find out from the fluidization characteristics of the powder how much air you require, and from that you can calculate what should be the size of your blower. But rat hole in ESP hopper is a common phenomena, and whether there is a rat hole or powder sticking to the wall or not, by looking in the vacuum versus time diagram of the ESP of the vacuum system, you can actually find out. You can guess that what's exactly happening. Sometimes the vacuum just doesn't build up after a few initial seconds, and you know that possibly there is some buildup of ash which is happening. I'm going to skip this particular one because of the lack of time, and I'm going to come to this one. I just wanted to share right now. We have got some very sophisticated instruments, very new instruments in our laboratory. First time we purchased that in India, which are known as GRANU drum, and I'm going to also share with you GRANU heap. So we are doing some tests and comparing the ESP fast field ash with second field ash, and these instruments tell us that how cohesive the ash is. So they have very good image processing software inside, and one of my PhD students is working on this, and we are seeing that by what new characterization tools we can have to understand the flowability of ash. So the larger dynamic angle of repose implies more cohesion. Then we also have static angle of repose, just like the dynamic angle of repose. Again, the larger the larger the triangle, the angles, we know it's more cohesive. So this is something towards the end I also wanted to share with you some of the latest research that we are doing. So with this, I come to the end of my presentation. So in the end, I would say, do not assume the ash properties. Ash properties can vary quite significantly, and don't assume them. You get your ash properties tested, do some flow property analysis, because if you don't do that, and if by any chance the ash is very cohesive for whatever reason, you might end up having a chronic suffering later. I mean, you might have to do so many things at the plant and still the ash may not come out. So a little bit of test in the beginning would actually, and some design check would actually save you from a lot of suffering in the end. And a good, well-designed system, ESP hopper flow system, would ensure that at least the ash is coming in the line, and then the vacuum and the pressure system, it's their responsibility then to make sure that the ash reaches the desired destination. So with this, I have come to my presentation. So I thank you for your patience. And if you have any query, you can write on the chat box and we'll take some of the queries in the end. And my next presenter is Professor Peter Whippich from University of Wollongong, Australia. And he is very, very reputed in this field. He has over 45, I think 40 to 45 years of experience of pneumatic conveying, flow property, etc. And he's going to talk about the flow assistance technologies that are available in hoppers. So if the ash is not coming out, then what to do? So he's going to talk about that. So with this, I invite Professor Whippich on board. Thank you again. Peter, it's your show now.
Thank you. Can you see that, Dr. Malik?
No, we can't see yet. But that's okay. You can take a little time. That's all right. These things happen.
Oh, hang on. I didn't press the button properly.
No problem, Professor Whippich. Yeah, it's coming now. It's about to come, I guess.
That's it.
Yeah, perfect.
Okay.
Perfect. Here you
Thanks,
go, Peter.
Dr. Malik, and thank you for your talk. It was a good introduction for flow properties, dealing with ESP Hopper flow problems. And very warm welcome and greetings from Australia. It's been, or still currently, it's almost sunset here, and it's 35 degrees. So very warm welcome. And just as an update, the cricketers are at tea, and India's 407. Maybe I shouldn't have said that. Everyone will disappear now. But anyway, welcome. Hopefully by the time I end my talk, they may be resuming for the last session, and you might, I'm not sure if they're screening that in India, but we're very thankful for the Indian team being here in Australia and giving us some enjoyment of Test cricket and also the previous one-day and T20 competitions. All right, anyway, we'll talk about a more interesting problem, hopper ash flow, and talking about flow promotion. So the first thing I'd like to really mention here and emphasize that ESP hoppers, it doesn't matter, all around the world, they are not designed for storage. All right, so, you know, we see these in Queensland, Australia, we see them in India or in China. They all look the same, very pyramidal looking hoppers, all have similar angles, and they're not designed for storage. And that's why we see these flow problems like Dr. Malik has shown us, and we'll see some more. And whether you've got blow tank discharge or screw conveyor, air slide, vacuum conveying at the bottom of these hoppers are not designed for storage. But for various reasons, of course, the operators, the plant operators and owners, they end up wishing to store the ash in these hoppers. So these hoppers are really only good for transferring the ash from the ESP or maybe baghouse down into your feeding or discharge system. And the fact that we end up, for those various reasons, we end up storing the ash in these hoppers, that's where you do see flow problems. So what are the consequences? Well, apart from, you know, rat holes and arching and stuff like that, you can actually get some significant loads occurring in these hoppers, and as these hoppers are not designed for storage, they can fail. Here we see some catastrophic failure of the hopper itself. This is one I visited over in China a number of years ago, and I haven't seen any in India, but hopefully that this is not happening, but it looks like it may be a common occurrence around the world. So when you get a case of a hopper failure, it's pretty bad, pretty catastrophic, as you can see. But when the whole ESP fails, that's getting really concerning. You hear this, you see the structure in the middle here, that whole ESP has collapsed due to the ash being stored in the hoppers. All right, so we'd like to really think about these hoppers and apply some modern design philosophy to try and get them to work better. Now, from the design, to try and do this from square one is virtually impossible, because ESPs are designed and built by ESP people, and they're not, and the hoppers are not designed by hopper experts. But I'd like to just share with you in this, if we're looking at requirements for reliable supply, what are the steps we've got to look at? And it's mainly from a troubleshooting perspective. So firstly, yes, we do need to know something about the characteristics of our ash, and we do need to know something about our flow properties, and Dr. Malik already shared some of that stuff with us. We need to understand our flow obstructions and flow patterns. And the most important step is to apply a systems approach to design by integrating the storage facilities with your feeding and conveying systems. So we can identify where your bottlenecks are, the interdependencies, what component affects what, and also very important area, often overlooked, is the interface between your storage system, your hopper, and your subsequent discharge or feeding system, because quite often on their own these components can operate quite well, but I've seen in my experience when they come together they don't like each other and they don't work well together. The next step, important step, is to estimate your loads. So you can see the consequences of not doing this work properly, as I showed in the previous slides. So if we don't allow for those loads occurring in those hoppers, not just the dead loads, but you can also get the non-symmetrical stresses because we clean out our hoppers in a sequence, and of course you get an uneven stress in our structure, and this is where these catastrophic failures can occur if the structural people have not allowed for this type of non-symmetry load. And the last step, quite often the little things in life make the big difference, and that's to pay attention to detail. So let's, not have ledges, avoid our ledges inside our hoppers. Dr. Malik showed a slide there with a pipe protruding into the hopper. You do not do that. Any ledge or protrusion is a place where material can stick and build up on, and that will contribute to the formation of your arch or dead zones that will contribute to your rat hole problem. So also we need to select and match our components to the material and application, and also pursue the acquisition of quality components matched to the product and application again. So flow properties, the way we measure that is a little bit different than Dr. Malik. The end result is pretty much the same. So with a direct shear tester, just very quickly, we measure our compressibility of the sample, the powder sample, or measure bulk density versus stress. We look at the internal friction. That's important, but more important is the wall friction. So you can see here wall friction varying quite a lot based on what wall material that we select. So, from a rectification point of view, this is an option, but the problem I find is with ESPs, you've got so many hoppers. So if you fix one hopper, you've got to do the whole lot of them, and that can become a very time-consuming and expensive exercise. And the last one is the flow function. Dr. Malik mentioned this briefly before. It looks at the sort of internal strength of the bulk material versus the applied consolidation stress or principal stress. All right, so these are your typical flow properties that we measure in Australia, a direct shear tester, but you get a similar sort of thing from the PFT. The most important thing to remember from this sort of information is that this type of flow property information is very dangerous to extrapolate or assume anything when it comes to flow properties. So, for example, what I'm showing you here in this slide is quite suitable for the design or troubleshooting of a mass flow bin and hopper. But if you're looking at a funnel flow system, and most ESP hoppers are funnel flow, then we need to actually measure these flow properties at higher stresses, perhaps up to 100 or 200 kilopascals. So extrapolating that sort of information out to the right, if you like, can be quite dangerous and misleading. So you should try and measure appropriate to the application conditions. All right, enough on flow properties. What do we use those? What do we use that information for? Well, hopefully we can use it and to avoid flow obstruction. So that information is useful to allow us to determine the hopper geometry parameters that will avoid a cohesive arch forming. And Dr. Malik showed a nice example of that previously. So the flow property information will help us avoid that flow obstruction. The more common flow obstruction is the rat hole in ESP hoppers. So this is where you get this central core flow down the middle. The material flows off the top, and unfortunately not all that comes out, and you're left with this stable pipe or rat hole. So the material that you see here becomes dead. It'll cool down and will gain strength over time, and it just gets harder and harder to shift the longer you leave it. A compromised design, the third flow obstruction is just material buildup. And that could be due to poor hopper design, incorrect selection of your wall materials, or there could be protrusions or ledges, and that's where material will build up over time, and you could end up getting a pseudo type rat hole at the end of the day as well. So with the flow properties, we can avoid these flow obstructions. And these rat holes are fairly common in the ash industry. And they also can be very stable. So I've seen, even with multiple outlet hoppers or bins, these rat holes can be very close together. And so the material in here in between is quite strong, and these rat holes can be quite stable, and they can be quite deep too. It can be several meters tall, these rat holes. All right, the second area that flow properties are useful for, and that's to achieve a reliable flow pattern. So we can design a mass flow bin, as Dr. Malik introduced previously, but I have not seen mass flow bins with ash because they're just too tall. What's more common is the funnel flow bin. And so with flow properties, again, we can design a reliable funnel flow bin. Now, what I mean by reliable funnel flow bin is that, okay, when we open up, we get no flow obstruction, that's good. All the material starts to flow, but all of it comes out. So the material you can see here flowing from the top out. So this last bit on the hopper here is the last to come out. But if we design the funnel flow properly, yes, it will all come out. An interesting hybrid version where we have a small section of mass flow down the bottom and funnel flow at the top, we call that an expanded flow bin. We have used this a little bit in some ash plants, but it's not common because it's very hard to modify so many ESP hoppers. But the critical design parameter here for expanded flow bin and also funnel flow bin is what we call the critical rat hole diameter. So from the flow property work, we determine what that number is. And so we can determine the design of an expanded flow bin as shown. Also, we can apply that to a funnel flow bin. So if we make sure our outlet is larger than the critical rat hole diameter, then that will ensure all the product comes out of that bin. So you get complete clean out. And really, this is what our objective should be, you know, whether it's mass flow, funnel flow, or expanded flow. So when we open the outlet, we get a flow initially, and then all the material comes out. And you know, if you're designing, you're putting your money in there to buy a 100-ton silo or a whole bunch of silos or hoppers, then you expect to recover 100 tons of material. But unfortunately, there's a lot of hoppers out there and bins that don't give you that return. We'd like to achieve that complete clean out, if possible, by gravity. You know, that's about the only thing on Earth that I find is free. Gravity. It's available to all of us in Australia, to India, in China, etc., etc. And we might as well use it to get that complete clean out. But if we don't get that complete clean out, then like Dr. Malik showed us earlier, we have to resort to a whole range of activities. And I guess you could call these flow promotion activities, but these can be quite dangerous. But, you know, getting out the hammers, the crowbars, the jackhammers, climbing up ladders to get access, etc., etc. So, you know, these activities can be quite dangerous. But, you know, this is only a cartoon, isn't it? It doesn't really happen in practice, does it? Well, all you got to do is look around, and it's amazing what you find. You can walk along and you see these things lying on the floor, and you think, wow, well, what are these things used for? You got a short one over here, you got a medium length, you got a long one. You always have a shovel and a bucket. You always have that. But look at the ends of some of these crowbars. You know, you've got a rectangular shaped plate there. This one's got a triangular one, and maybe one's used for Monday, Tuesday, Wednesday. I don't know. But, you know, this is obviously evidence that some of this activity does occur out in industry. So I guess you could call these tools of the trade, flow promotion tools of the trade. And what are the consequences of this type of flow promotion activity? Well, I guess you can call this impactus dermatitis that you'll see out in industry. Maybe you see this in your own plant. It's good evidence of this type of flow promotion activity occurring. Now have a look at this hopper for a moment. You know, this hopper is very steep, you know, and why doesn't the ash come out? Why doesn't it come out? Well, it could be the valve obstructing the flow. It could be the gasket protruding into the hopper at the outlet. That's the most sensitive part of the hopper, at the outlet where your stresses are low. So any small obstruction there or protrusion can be catastrophic. You know, the material will just arch up. Or maybe it could be these sockets, air injection sockets that have been pushed in too far and welded up. They could be protruding. So it could be a number of these. It could be all those things. The end result is, yeah, we've got a flow problem, and there's the evidence. And the thing I find with operators out there, they don't know when to stop. They will just keep heading away, and they can transform the shape from a nice round conical smooth hopper to, I don't know what you call that, polygon shaped sort of hopper. But you got to realize, you know, you're getting some sharp corners and valleys in there now, and that just exacerbates the problem. So, you know, these are, I suppose you call flow promotion activities, but they're not the ones we recommend, obviously. All right, anyway, so we maybe can move on to something a bit more sophisticated. Let's have a look at some space age technology. So I've seen examples of this in Australia where people have actually, you know, taken the concept of a flying saucer, attached it to a cable, and in this part of the plant, when they had a flow obstruction, they used to climb up on the ladder and hit it with a hammer. And then a man fell off and injured himself. So a smart guy came up with this idea. So you can actually, at ground level, hold on to this flying saucer and give the bin an almighty whack. And you can see a strategically placed impact plate there. And they think, oh, wow, we got some success. The materials flowed. Oh, wow. Okay, well, let's put them everywhere. So we got one there, another one there, another one there, and they're all throughout the whole plant. I recommend this? Not really, but it's amazing just to show you the sort of things that people come up with. Oh, let's move into semi-automation. That's the industry buzzword these days, automation, isn't it? Okay, so yeah, Jackhammer is a semi-automated flow promotion device. I mean, these are not ESP hoppers, obviously, but again, we've got strategically placed impact plates along here, and away we go with our semi-automated impact system or flow promotion device. And we can go to full automation, put on vibrators. So, you know, to try and get this arch to fail, whack on a vibrator on the side here, and away we go. But, you know, where do we place the vibrator? That's an interesting question. And that can make an important difference. And also, are these vibrators suitable for this purpose? Well, I asked a question. To answer that question, we'll ask a question. What do we use vibration in road building for? On road base, we use vibration to consolidate the material to make it stronger. So the thing is, if we apply a vibrator to a situation like this, we've got an arch. And if the arch does not fail, maybe the frequency, amplitude of the vibration signal is not suitable, maybe the location is not suitable. Then if this arch does not fail, then guess what will happen to your bolt material? It will get stronger. You'll make the situation worse. So all I'm suggesting here, be careful about when you start whacking on vibrators onto your hoppers. They can be useful, but generally I will only put on the vibrator when we have established flow. So that we open the valve down the bottom here, or start the feeder, we get flow, then we can put on vibration to assist flow. So if we put on vibration to initiate flow and we don't get it, then you're gonna make the whole thing worse. All right, so the other issue about vibration too, I found, is that some people get some success and they think, well, okay, next time it doesn't work, we'll put on a bigger vibrator and the bigger vibrator, and you end up starting to crack the bin from fatigue damage. So you can see here some cracks appearing and the whole bin is starting to fail because of the vibrator. So that's the other consequence of putting on too much vibration. So be careful. Aeration systems, these are quite common. Putting on hoppers, a manifold, lots of injection points and hoses, put on some compressed air or pressurized air, and then to aerate the material to hopefully initiate flow and maintain flow. So the questions we have to ask here, if we're going to try and get this thing to work, is how many injection points do we need? You know, do we have enough in this particular installation? You know, we can see here a bit of impact dermatitis over here. Maybe not. Maybe we need some more over here. How much air do we need? Maybe the airflow is insufficient here. Maybe we have to increase the air pressure to blow a bit more air through. And, you know, where will the air go? That's an interesting question. No one knows. You turn on the air, you'll hear a bit of hissing. The air's going somewhere. Maybe it's all spewing out of this broken hose here out in the atmosphere, and nothing's coming into the hopper. Maybe it's all blowing down through the bottom here where the stresses inside the bin are the lowest, and there's not much coming out the top. So this is one of the problems with such a manifold multi-point injection system. To try and get even distribution, which is a desirable feature, is very difficult in practice. And there are some little tricks you can do with orifice plates, but this really does complicate your whole sort of solution approach with this type of technology. Maybe we can use aeration pads or membranes. These are more common, I guess, in hoppers. Some of the things you have to be aware of, you have to now understand more about the fluidisation characteristics of your powder. And so depending on those fluidisation characteristics, when you put injection air into such porous pads or membranes, two things can happen. Either, yep, you can expand your powder, which is what's needed, you reduce its strength and it'll enhance the flow. Or you can just blow holes through it and form rat holes due to the cohesive nature of that material. And the air will just take the easy path out. And I've seen this happen in hoppers many times. I've also seen this happen in blow tanks. So just to understand the differences here, these are just 5 different fly ash samples we tested many years ago, and we did some fluidisation work. Ash 1 and 2 here, they fluidise beautifully. Minimum fluidisation velocity is quite low, and you might end up using through your pad a fluidisation velocity around about 2 or 3 centimetres per second, and that works. So these ash samples here, 1 and 2, fluidise quite nicely. 3, 4, and 5 are poor fluidisation materials. They channel, and these will be more susceptible to rat holing if you inject air into them. So you have to be really careful how you inject the air. So you might need a larger pad surface area to try and fluidise more of the material. And this is where your even distribution of airflow is quite important. So if you have ash 3, 4, and 5, you may need a fluidisation velocity around about, or aeration velocity, I should say, around about 8 or 10 centimetres per second, as opposed to 2 or 3 for fly ash samples 1 and 2. So this sort of information is useful, certainly from a design perspective, but also a troubleshooting perspective. It gives us some idea what our options are when you're applying it into the plant. Anyway, let's get serious. The last aeration system I'll cover, and it's getting close to the end of my talk, air cannons. Dr. Mallet mentioned it briefly. I've seen these used quite a lot around the place. And so, you know, there's the old story. We've got an arching problem or rat holing problem. The guy in the plant rings up the air cannon supplier. Said, yeah, no worries, mate. We'll put 3 of them here, 1 in there and a couple of down the bottom, and just blast away when you get a problem. And yes, it works. And suddenly the arch is up here. And so the guy at the plant, he rings up the supplier. Supplier says, yeah, no worries, mate. We'll sell you more. We'll sell you more. Don't worry. Don't worry. We'll be happy to take your money. And you end up getting a Christmas tree, which is, I suppose, appropriate this time of year. But really, what you have to understand here, in the end, yes, you put enough of these on, they will work. But we're only really treating the symptom. And sometimes that is necessary, certainly for ESP Hopper type applications. But really, our preference is a root cause solution. Trying to identify what the root cause problem is, and then finding out what your solution options are. Not always possible, and so we do certainly rely on flow promotion. But how you apply that flow promotion, you don't want to jump in feet first. You want to think about the problem and what is the best solution for that flow problem. In this particular case, for the bin on the right, the interface down here between the hopper and the feeder was the problem. And once that was rectified, all those air cannons became useless. So that was where a root cause solution was possible, and it was obtained. But anyway, just some food for thought. I hope you find that useful. I don't know the cricket score. I'm not allowed to use my mobile phone when I'm presenting. But anyway, I'm sure someone will let us know during the course of the evening. So I hope you found that interesting. And I look forward to any questions that you may have later on. So for the moment, thank you very much for your attention. Back to you, Dr. Malley.
Yeah, thank you, Peter, for your presentation. So we are going to now come to the question and answer session. Okay, Peter, we start with a question for you, which is what aeration system is most reliable?
Okay. A very simple question, not that easy to answer. I mean, in my experience with ESP hoppers and some of these photos that you showed, Dr. Mallet, you can see there's quite a bit of ash there built up, dead regions. So in principle, what we'd like to do is get something in there that will agitate that material. And once you agitate it at the appropriate time, then you can get the material to flow out and discharge. And so you want something that's reliable. Now, if you start just putting on some hoses and injection points, those systems are doomed for failure, because the ash will work its way back up. And if you've got not check valves, little on-off valves, or anything like that, diaphragm valves to actuate, the ash will work its way back up that system. So you need some sort of physical barrier. So in general, we prefer some sort of pad, metal pad system. These, however, are always difficult to install, because you have to really shut down your ESP, get inside and start making major modifications. You also got all that cladding on the outside you have to somehow get through. Some success that we've had in Australia is to put on what we call a hopper pulse valve. And you can actually install these in situ. You've got something like a 1.5 2-inch threaded pipe fitting socket that you put on the outside of your hopper. You can actually then in situ drill out the hole, and then you can put in this hopper pulse valve. Now, a hopper pulse valve is like just nothing more than a poppet valve. So it sits flush to the inside of your hopper, and the protrusion is only a little stainless steel poppet. It's about a 2-inch diameter sort of poppet, and these only open up under compressed air, and there's compressed air behind it all the time, so there's no risk of ash flowing back into that chamber to stuff up the operations of your valve. So the poppet only opens briefly, and also only goes up a fraction of a millimeter. And you can control the on and off time for you, and you can sequence around your hoppers. So we've done these on hoppers. We've also done them on blow tanks. And what the poppet does, it shoots compressed air out on the hopper wall. So what it helps to do is to fluidize the material on the wall, and in front of the poppet, it actually sucks the ash into it. We've got a demonstration hopper in our lab that shows you these principles of operation. And so the end result is you get that sort of agitation of material, you get that washing down effect on the wall. That's where you want the ash to flow. And yeah, that's probably one of the best devices I've seen, and that can work in this sort of application, also for high temperature application. So, but I don't know if you can get this sort of device over in India. Someone would have to do some digging to find out. Anyway, I hope that answers that question.
There is one more question for me, which is why the ash would consolidate over time. I think the reason is when you keep the ash under stress, the particle to particle distance goes down, and the surface irregularities also could be getting crushed. So the average distance between the particles would decrease. So that would increase the van der Waals forces between the particles. Also, if there is some moisture, now the moisture, the breach formation would be more with time. So these are some of the reasons why with time the powders would get more consolidated. There was one more question related to bottom ash, but in this today, unfortunately, in this webinar, we are not dealing with bottom ash. So we'll take your question, or we'll discuss on that when we do a webinar related to bottom ash flow or transport. So now I would go to the concluding. We are going to go to the concluding session of our webinar, and I would like to invite Mr. D.S. Mollik, who is also a director of Bulk Solids Innovation India Private Limited. Mr. D.S. Mollik has worked for 45 years in DCPL Development Consultants and DCIPS as the general manager, and he has a vast experience of bulk material handling. He has also been at some stage, he has also been an advisor to the Ministry of Power, Government of India, and he was he's part of many IS committees on material handling. So, Mr. Mollik, I would invite you to give your concluding remarks.
Good afternoon. Thank you all. Thank you for your patience hearing. And now to conclude in one or two sentences, what I can tell that very often ash is not flowing and the blame is put on the ash handling contractor. This has been the general practice. But by virtue of my visits to different plants, I have seen that in there are cases where the poor fellow is the ash handling contractor. He is not getting the flow, and that is why, in spite of his design being adequate, he is not able to show his design, and there has been accumulation of ash in the ESP hoppers. So the one fundamental thing what has to be considered is that whatever ash is generated in ESP, that has to go outside, and then subsequently the ash handling contractor can take it forward. But there are many instances where this does not happen. There can be many reasons. One reason can be that proper slope angle has not been provided. But again, there can be controversy in that because even if you provide a very high valley angle, say 75 degree, 80 degree, in spite of that, you can land up into problem. As Dr. Waipak told, that there can be very silly things against which the problem can start, and then it can really accumulate and then can completely choke the hopper, like the protrusion of the air lines, fluidizing lines, or the protrusion of the gaskets. These are very silly things, but this can start as an initiator, and subsequently the entire thing can be choked. So starting the model study, starting the flow study or through the hopper alone is not enough. And moreover, one common theory nowadays is coming that let us go for model study. That's very good. I think that has not been yet attempted, but that is good. Like for example, for big intake pump house, the model study is conducted, even though Hydraulic Institute standard has very good guidelines, but still they ultimately tell that it has to be vetted by a model study, and the model scale of modeling is also identified 1:10. In similar way, the ESP hopper also can be modeled and can found out that whether proper flow is being achieved. But there are many questions here, that what will be the scale of operation, 1:10 or something 1:15, and whatever results we are getting through the model study, how that can be interpreted for the actual case. For hydraulics, this has been established after lots years of research, that what should be the velocity and other criteria, so that the model exactly replicates the true situation. But that much of research has not yet been put in the field of particle science. So maybe it will take some more time before we can really come out with some solutions with modeling. And to add to it, even if you make a first-class hopper with very smooth flow, again very small things can lead to the creation of this choking, initiation of choking, and ultimately can bridge the entire thing. So it's a very difficult science, and one has to be very careful about designing these hoppers, and making some flow assisting devices has to be also looked into, so that in case natural flow or the gravity flow ceases, then we can put them into operation. Again, I tell you, this is a science which is coming up. Not many research papers are available, not many recommendations are also available. So one has to do a very hard work to find out the science of this flow pattern, particularly for ESP Ash, where cohesion is a very important criteria, where electrostatic forces is very important criteria. So all this together, I think it will take a few very dedicated research to find out the ultimate solution, as has come out for hydraulic flow study, and which is already established, and if you follow that, you will automatically get the actual flow pattern. The same way, we have to do a lot to find out some clear-cut solutions in this regard. Thank you. Thank you.
Okay, thank you, Mr. Malli. And finally, I thank all the participants. Our contact is given here, Bulk Solids Innovation India Private Limited. We are once again placed at Thapar Institute campus. And you can reach to us either by writing an email to director@bulksolidsindia.com or simply to ssmallik@thapar.edu. I thank all of you for your patient listening, and I hope today's webinar has increased your understanding about the science of this flow property subject and what are the possible solutions that can be put in place to achieve the desired result. I thank all my colleagues and Professor Vipich for your time and sharing the knowledge with us. Thank you very much.
Thank you. It's been a pleasure. And Coley's got his half century. So
Thank you. Thank you for this message.
it's a good night. It's a good night. Good night, everyone. Thank you.
Okay. Good night.
Good night.